Dear students, let us continue our study after studying the electronic effects, their applications, and in this particular module we shall study about tautomerism. You are already aware with the tautomerism in a brief view, but here we will be going into a detailed in-depth study of tautomerism. After studying this module, you shall be able to know about tautomerism and its causes. You shall be able to learn about the acidic protons being the root cause of tautomerism and how it gives rise to the two forms having different functional groups. You shall be able to understand what are the factors which affect the different forms of tautomers and learn about some modern theories of tautomerism with suitable examples. Tautomers are isomers of a compound which differ only in the position of the protons and electrons. The carbon skeleton of the compound is unchanged, but functional groups are different. A reaction which involves simple proton transfer in an intramolecular fashion is called as a tautomerism. Keto-enol tautomerism is a very common example under this, and it can be acid as well as base catalyzed. Typically, the keto form of the compound is more stable, but in some instances the enol form can also be more stable. There are many types of tautomerisms, and let us try to understand tautomerism by first focusing on the keto-enol tautomerism, and later we will extend this understanding to other types of tautomerism. It is also important to understand the acidity of alpha hydrogen atoms to understand why tautomerism really takes place. So, first of all, let us know what is the acidity of alpha hydrogen, which is the cause of tautomerism. As you are aware, aldehydes and ketones are weak acids and they have abnormally low pKa values between 15 and 20. Therefore, they can behave as a Bronsted acid in an acid base reaction with a strong base. But aldehydes and ketones are much stronger acids than alkanes. As there is hardly any electronegative difference between hydrogen and carbon, the CH bonds in alkanes are almost non-polarized. Therefore, hydrogens in alkanes are not acidic. The values of pKa of alkanes are nearly around 50. And as you can see here, you can do this comparison that ethane is shown where the pKa is 50, and you are shown with this acetone molecule where the pKa is 20 for these alpha hydrogens. And then there is this higher ketone where this CH2, the alpha hydrogens are further attached to CH3, the beta one. The pKa of the alpha hydrogen, notice it is 19 to 20. So, they are more acidic than the pKa of the beta hydrogens, which is 40 to 50. So, these beta hydrogens are behaving almost like alkanes, but the alpha hydrogens are more acidic. So, the alpha hydrogens of aldehydes and ketones, we can say they are quite acidic as compared to the hydrogens of alkanes. The acidity of alpha hydrogens of aldehydes and ketones is although much less than carboxylic acid, where the pK values are around 3 to 4. Now, if we try to know what are the reasons for acidity of these alpha hydrogens, the alpha hydrogen of carbonyl compounds are acidic as these are connected with the alpha carbon, which is further directly bound to the electron withdrawing carbonyl group. The high acidity of carbonyl compounds as compared to alkanes can be explained by the resonance stabilization of the conjugate base by the carbonyl group after it is formed via the deprotonation, or in other words we can say it is the anion stabilization after the deprotonation. The anion is also known as enolate anion, and due to resonance the negative charge is mostly dispersed between the alpha carbon and the carbonyl oxygen by resonance, which leads to stabilization of the otherwise highly energized carbanion. The negative charge and the nucleophilic qualities are hence distributed at the carbon in case of alpha carbanion and at the oxygen when it is in the form of the enolate anion. As a result, the alpha carbon and the carbonyl oxygen are the two nucleophilic and basic centers of these species, which is the enolate anion. And as you can see here, shown that this is the alpha carbon joined to this hydrogen, and once this alpha hydrogen is removed, there will be formation of negative charge over carbon. This is the alpha carbanion, and after the delocalization it will give rise to enolate ion where the negative charge is residing on the oxygen. Now, if we look at the variation of acidity, the acidities of these alpha hydrogen atoms is enhanced if an electron withdrawing group is attached to the alpha carbon atom. So, this you can see here that to this very particular alpha carbon, if you have electron withdrawing group, obviously the electron withdrawing power of the alpha carbon is further enhanced and it will help in making this hydrogen even more acidic. On the other hand, the acidity of the alpha hydrogen atoms will be decreasing if there are electron donating groups which are attached to the alpha carbon, as you can see here. So, this electron releasing group or the electron donating group G here will be making this alpha carbon less electron withdrawing, and thereby the acidity of this alpha hydrogen will be decreasing. So, now keeping this basic understanding as the background understanding, let us now move to detail of keto-enol tautomerism. The keto form and the enolic form, when they are in equilibrium, is called as the keto-enol tautomerism. As you can see in this equilibrium reaction, that is, you have this RCH2COR, and in the presence of water this proton can be taken out and you get the enol form, and this equilibrium can be established, it can be catalyzed by both acids as well as bases through the suitable means such as by fractional crystallization or careful distillation. In the absence of any acid and any base, the keto and enolic form may be separated from each other. The keto and enolic form of a carbonyl compound, they are the constitutional isomers or the structural isomers. The separation should take place in the absence of all acids and bases, because the equilibrium reaction would otherwise proceed too rapidly and it will be difficult for the separation to be achieved. Therefore, the separated pure keto and the pure enolic form would immediately be contaminated at least to some degree by the other form again. So, you have to keep in mind that once you have separated, you have to keep them away from acid or base contamination. Now, let us look at the equilibrium position in keto-enol tautomerism. The position of the keto-enol equilibrium is influenced by the temperature and the solvent if present. In case of simple aldehydes and ketones, the keto form usually exceeds the enolic form to a considerable degree. For example, if we consider the case of acetone, acetone contains only 1.5 into 10 raised per minus 4 percentage of the enolic form, which is very less. So, predominantly it is the keto form in acetone. Ketones are usually not enolized to such a degree as the aldehydes are. However, if we talk about beta-dicarbonyl compounds, they are significantly much more enolized, as the double bond of the mono-enolized beta-dicarbonyl compound is additionally stabilized through resonance with the second carbonyl group, and as a result the alpha hydrogen between the two carbonyl groups of the beta-dicarbonyl compounds is much more acidic. On the other extreme, The classic example of a compound that is virtually completely enolized is, you can guess, it is phenol. The equilibrium constant of the keto-enol tautomerism equilibrium of phenol amounts to roughly 10 raised per 10. It follows that the enolic form of phenol predominates to over 99.99%. The enolic form of phenol, which is aromatic, is much more stable than the non-aromatic keto form, which is cyclohexadienone. And this is due to the strikingly high resonance stabilization of the aromatic system, which is possible when it is in enol form, that is in the phenol, and not in the keto form. Also, the phenol's enolate is much more stable than the non-aromatic enolates are, as its negative charge is further stabilized through resonance with the aromatic system. And as a result, phenol is considerably more acidic than other enols or alcohols, and this you are already aware. The pK value of phenol is 9.95, and you can clearly see here how this keto and enol form of phenol is shown, and you can clearly make out the keto form of phenol is less stable because of non-aromaticity, and in case of the enolic form of phenol, where it exists in 99.99%, is more stable because of the aromaticity. After this, let us focus more on the beta-dicarbonyl compounds. The acidity of beta-dicarbonyl compounds is considerably higher than that of the monocarbonyl compounds and other dicarbonyl compounds. In keto-enol equilibrium of beta-dicarbonyl compounds, the monoenolic form usually exceeds the keto form. For example, the 2,4-pentadienone consists of about 76% enolic form, and there is 24% keto form, as you can see here. So, this is the enol form, which is 76%, and this is the keto form, the dicarbonyl, where the pK is 8.9, and you can notice the enol form can be involving either this carbonyl or this carbonyl. So, correspondingly, these are the two enolic form which can be exhibited. The reason for this is the noticeably higher stabilization of the enol in comparison to other carbonyl compounds. On the one hand, a beta dicarbonyl compound's enol is additionally stabilized through resonance of the enol's carbon-carbon double bond with the second carbonyl group, and on the other hand, the enol's hydroxyl hydrogen bonding is connected to the carbonyl oxygen by an intramolecular hydrogen bond, as you can see in this structure. The formation of this hydrogen bond is further facilitated by the 6-membered planar structure of the enol carbonyl resonance system, which will be helping in stabilization. After this, let us now take one particular case, which is ethyl acetoacetate, that is how the keto-enol tautomerism is there in case of ethyl acetoacetate. Acetic ester or ethyl acetoacetate is the ethyl ester of acetoacetic acid, and it is a beta ketonic acid, which is acetoacetic acid. Acetoacetic ester was first discovered by Goethe in 1863, who prepared it by the action of sodium on ethyl acetate, and he gave the formula as shown here, that is CH3COH double bond CH COO C2H5, that is the beta hydroxycrotonic ester. Later in 1865, Franklin and Dupas also prepared acetoacetic ester by the action of sodium on ethyl acetate, but they proposed a different formula for this compound as CH3COCH2COOC2H5. In 1863, Goethe gave the enol form as the structure, and in 1865 the two scientists Franklin and Dupa, they gave the keto form, that is the beta ketobutyric ester. So the question now comes, which of these is correct? Now if you look at the evidence in favor of the Guether formula, which are there corresponding to the reactions of an unsaturated alcohol. First is, when acetoacetic ester is treated with sodium, hydrogen is evolved and the sodium derivative is formed, and this showed the presence of a hydroxyl group. Second evidence is, when acetoacetic ester is treated with an ethanolic solution of bromine, it readily decolorizes. This indicates the presence of an olefinic double bond, which will not be exhibited by the keto form, but only by this enol form having double bond. Further, when acetoacetic ester is treated with ferric chloride, a reddish violet color is produced, and this is a characteristic of compounds which contain the enolic group, like you are already aware, this is a test used for phenols also. But then there are evidences which are in favor of the Franklin-Dupa formula, that is the reactions of a typical reactions of a ketone. Like first, with sodium hydrogen sulfide, it forms a bisulfide derivative. Now this is a reaction specific for carbonyl and not for the enol structure. Similarly, with hydrogen cyanide, acetoacetic ester forms a cyanohydrin. This is again a typical reaction of a ketone and not given by enol. So thus there were evidence for both the structures, and the controversy continued until about 1910, when chemists came to the conclusion that actually both the formulas were correct and that the two compounds existed together in equilibrium in solution or in the liquid state, and because of existence in both the forms, all these reactions were given, and you can see the equilibrium will be through this keto into the enol form of this compound. When a reagent which reacts with ketones is added to acetoacetic ester, the ketone form is removed and this upsets the equilibrium, and in order to restore the equilibrium mixture, the hydroxyl form of the acetoacetic ester changes into the ketone form, and thus the provided insufficient reagent is added, the acetoacetic ester reacts completely as the ketone form. Similarly, when a reagent which reacts with olefins or with hydroxy compounds is added in insufficient quantity, acetoacetic ester reacts completely as the hydroxyl form. And in 1911, Knorr succeeded in isolating both these forms. Let us see how the ketone form was isolated. On cooling a solution of acetoacetic ester in light petrol to -78 degrees centigrade, he obtained crystals which melted at -39 degrees centigrade. And this substance gave no coloration with ferric chloride and did not combine with bromine, and was therefore regarded as the pure ketone form corresponding to the Franklin-Dupa formula. Let us see how Knorr isolated the hydroxyl form. He did so by suspending the sodium derivative of acetoacetic ester in light petrol cooled to -78 degrees centigrade, and then treating this suspension with just enough HCl to decompose the sodium salt. He obtained a glassy solid when cooled. This substance gave an intense coloration with ferric chloride and was therefore the pure hydroxyl form corresponding to the Guether formula. Thus, acetoacetic ester is a substance that does the duty of two structural isomers, each isomer being capable of changing rapidly into the other when the equilibrium is disturbed, for example by the addition of certain reagents. And this is the case of dynamic isomerism, and the name tautomerism, if you look at the Greek word, it means same parts. It was given to this phenomena by Law in 1885. The two forms are known as tautomers or tautomerides, the phenomena being called as keto-enol tautomerism. Note that the term enol is a combination of "-ene" for the double bond and "-ol" for the hydroxyl group. So, after the case of acetoacetic ester, I am sure that you are now clear about how the tautomers are in dynamic equilibrium with each other. So, actually they are containing different functional group, but they are readily interconvertible. It is not just to any two functional group, but yes, the positioning of hydrogen, the active alpha hydrogen from one position to other is giving rise to the change in functional group, and they are yet in dynamic equilibrium, which is very important for them to be called as tautomers. So, let us now look at the stability aspect of tautomers. When one tautomer is more stable than the other under ordinary conditions, the former is known as the stable form and the later is known as the labile form. It is generally difficult to say which is the labile form, since very often a slight change in the conditions, for example temperature, solvent, etc., will shift the equilibrium from the keto to enol or vice versa. Tautomerism in the solid state is rare, and hence in the solid state one or other tautomer is normally stable, but in the liquid or gaseous state or in solution, the two forms usually they exist as an equilibrium mixture. It has been found that the enol form is more volatile than the keto form. The change from enol to keto is extremely sensitive to catalysts like acids or bases. Experiments using deuterium exchange reactions have also shown the presence of keto-enol mixtures. Shown here is the table which shows the percentage of enol content, and you can clearly see here the different compounds which are shown against the percentage enol content in them. First you have the CH3CO, CH2, COO, CH3 where the percentage enol content is 4.8. Similarly, the next one where you have ethyl acetoacetate having 7.5, CH3CO, CH2, CO, CH3, a dicarbonyl having 76. Then another dicarbonyl which is the substituted one, it has 31, and another dicarbonyl where both of these are phenyl, you can show it has been significantly higher to 96. Similarly, in case of simple aldehydes RCH2CHO, there is trace, the diethyl malonate is also trace, and the ketones of the type which are monocarbonyl, there is again trace amount of the enol content. Let us now look at the factors affecting the enol content. First is the ring strain. If the enol form is the intramolecularly hydrogen bonded, it is more stable and would lead to a higher enol content. Cyclic monoketones contain more enol content than the corresponding acyclic 2-ones. In the cyclic ketones, change from keto to enol involves a relatively small change in strain in the ring due to the introduction of a double bond. For acyclic ketones, the introduction of the double bond has a much greater effect on the freedom to take up different conformations. The next factor is the steric factor. The enol content of acetyl acetone is higher than alpha methyl acetyl acetone in gas phase. In the later compound, there is much greater steric repulsion due to the presence of the alpha methyl group. Thus, the alpha methyl enol, as you can see here, has greater internal strain than the enol form of acetyl acetone. Coming to the nature of solvent, any solvent that can form hydrogen bonds with the carbonyl group of the keto form will stabilize this form by solvation. The enol form, however, since it forms an intramolecular bond, will be largely prevented from the formation of hydrogen bonds with the solvent, that is solvation will be less. Thus, the keto form is stabilized with respect to the enol form. For example, with solvents like water, methanol, acetic acid, they tend to reduce the enol content. On the other hand, in solvents which are non-polar and not capable of forming the hydrogen bond like hexane, benzene, etc., the enol content will be higher, and the keto content will be less. For example, the enol content of acetyl acetone in hexane is 92%. After this, let us look at the modern theories of tautomerism. Ingold in 1927 suggested the name ketonotrophy for all those cases of tautomerism which involve the separation of a cation. Lowry in 1923 suggested the name prototropy for those cases in which a proton separates and called such systems as prototropic systems, and it can be seen that prototropy is the special case of ketonotrophy. Ingold also suggested aninotrophy. He used this term aninotrophy for those cases which involve the separation of an anion. And later in 1944, Broad and Jones, they also proposed the term auxotropy for the aninotropic rearrangement involving only the migration of hydroxyl group. Let us now consider some examples which involve the prototropy and the aninotropy and some other types of tautomerism. Analogous to the keto-enol tautomerism, there are some other types of tautomerism involving other functional groups. Notice that here also mostly the acidic hydrogen is shifting from one position to another position within the same molecule, giving rise to another functional group, and yet the two forms are in dynamic equilibrium. So that is the basic requirement you can say for identifying tautomerism. So for example, look at this amide form and imidol form. So we can say this is the amide imidol tautomerism. In the amide you can say this is the CONH, the amide functional group is there, and as this hydrogen joined to the nitrogen shifts to the oxygen, we get this imidol form. You can see the imine is the C double bond N joined to the ol, that is how the name imidol. This is also called as amide imidic acid tautomerism. The next one is the lactam tautomerism, and you can again see here this is the lactam form which is the cyclic amide, and it is giving you the corresponding imidol form in the cyclic manner which is the lactam form. So the name lactam tautomerism. And for example, you can consider these are the two structures in the equilibrium. One you can see this is the imidol form and this is the amide form, and notice that here the imidol form will be much more stable because of the aromatic ring structure. Moving to yet another type of tautomerism is the amine tautomerism. Here you can see the amine form and which is aromatic, and in the imine form as the hydrogen from the nitrogen will migrate to another nitrogen, you get this imine form. So this one is not aromatic and will be comparatively less stable out of these two. Then we have annular tautomerism. This is a special case of prototropic tautomerism where a hydrogen atom can occupy two or more possible locations in a heterocyclic system. For example, indazole which can have 1H and 2H tautomers. So you can notice this is the 1H tautomerism where this particular nitrogen is joined to the hydrogen, and in the 2H tautomer it is the second position nitrogen which is joined to the hydrogen of the indazole. Then we also have valence tautomerism. Valence or valency, whatever way you are familiar with the pronunciation. Valence tautomerism is a type of tautomerism in which single and or double bonds are rapidly formed and ruptured without the migration of any atom or groups. It is different from prototropic tautomerism or the prototropy where you have the migration of hydrogen or proton, but here it is involving the process of rapid reorganization of only the bonding electrons without changing the structural part or the atoms of that particular molecule. It is also referred to as fluxional tautomerism. For example, notice that in this particular example, one is a 6-membered ring joined to 3-membered oxygen as the epoxide ring, and as these two electrons they migrate, you will be getting a 7-membered cyclic ring with oxygen in between. So, this is a case of fluxional tautomerism. Similarly, let us look at another example where you have 1,3,5 cyclooctatriene getting rearranged into bicyclo 4,2,0-octa-2,4-diene, and you can notice that there are no hydrogen, no carbon getting shifted, it is simply the electrons joining and you are getting this new structure. Let us now look at the non-prototropic tautomerism. In case of non-prototropic tautomerism, it involves the relocation of a substituent other than hydrogen. So, it is not only the hydrogen, a new substituent can change its position from here to here. So, for example, look at this particular case as shown here, the tautomerism of 1 and 2 N disubstituted amino-methyl benzotriazoles, and here you can see this particular group, that is CH2 joined to N, AR and methyl, this entirely is earlier in this particular case on this nitrogen, but then it shifts to the other nitrogen and gives rise to this particular case of tautomerism. Other forms of non-prototropic tautomerism include acylotropism, that is, as the name indicates, it is the transfer of the acyl group, that is why acylotropism, or it can be methylotropism, you have guessed it right, it will be the transfer of a methyl group, arylotropism where it will be transfer of an aryl group, transfer of even nitrogen groups, and elementotropism where there is a transfer of halogens and metals, that is of elements. Elementotropism includes chlorotropism if there is a transfer of chlorine, and metallotropism if there is a transfer of a metal atom or a metal containing group. We also have ring chain tautomerism. In ring chain tautomerism, a structural change occurs between an open chain form and a ring form through a hydrogen shift, and this is an important process for monosaccharides such as sugars. For example, as you can see here, glucose can exist in 5 different tautomeric forms in solution. What are these forms? It can be alpha D glucopyranose, it can be beta D glucopyranose, where in both of these there is a 6-membered ring formed where oxygen is a part of the 6-membered ring, that is a pyranose structure, or the ring closure can happen where you get 5-membered ring, that is it can be alpha D glucofuranose or beta D glucofuranose. Obviously, out of these the pyranose structures are more stable, but it will be able to exhibit in all these 5 forms, one the open ring form and other these 4 cyclic forms. So, dear students, I am sure now you are aware about the various forms of tautomerism, and it is not only the keto-enol tautomerism, but yes, studying the keto-enol tautomerism, we have understood how the alpha hydrogens, their acidity are the factors which will make this equilibrium, the dynamic equilibrium establish, and the 2 different functional groups arise on their own, or they can be initiated or catalyzed with the help of acids or bases. So, let us summarize what we have learnt in this module. We have learnt about tautomers, which are the isomers of a compound, and they differ in the position of protons and electrons. The carbon skeleton of the compound is unchanged in these, but the functional groups are different. The alpha hydrogen of carbonyl compounds is acidic. We have studied why it is acidic, and that is the main reason for the keto-enol tautomerism to occur. Furthermore, The establishment of the equilibrium may be catalyzed by both acids and bases, but through suitable means such as fractional crystallization or careful distillation. In the absence of any acid or base, the pure keto and the pure enolic form can be separated. All this we have discussed. And many scientists have suggested various forms and theories of tautomerism, and this module discusses an exhaustive list of these different types of tautomerism, including the ring chain tautomerism, the non-prototropic tautomerism, which is also referred to as fluxional tautomerism.